Lesson 19, the inverse is, yay, you're going to learn how to find the inverse of a function. So, for this opening exercise, we've got a domain and a range, and the argument is that the inverse is simply reversing the domain and range, right? So, for this one, we saw that we had a range, right? And remember, domain, you call this x and y, or x and f of x. The main gist of it, right, is that this is an input, and that is an output, right? That's the idea behind domain and range and function. So for this first one, we have a -2 that corresponds with this -2. And we have a 4, and that corresponds with this 4. So what have we done? We have a function that is reversing the domain and the range. And I'll give you an example of such a function here in a second. But if we're going to do what Eureka wants us to do and fill this in, this would make this 3, 1. Over there on the left-hand side, we have a output of 8. So that means our new output will be 3. It'll match the input of the previous one. We have 9, 5, and 15, 2. Well, why is that working? Why is it like that? What in the world does something like this? I will show you. I think I'm going to have more room. I'm going to do it here. All right, so if I had 1, 2, 3, 4, 5 as my domain, right? And then my range was 5, 10, 15, 20, right? So that's our map. I don't know why I put a 5 there. We're not going to use it. We're just going to go with 4. It turns out that I could think of a function that does this, right? This is my x and that's my y. Or say, let's use the term f of x. So let's call this f of x. So domain and range. What function, can you think of a function that would give me this type of scenario? I input 1, it outputs 5. I input 2, it outputs 10. I input 3, it outputs 5. What's the common? Yeah, original 5 and 5. So I could say f of x is 5x. That's the function that would give me that relationship, right? Okay, well, I'm going to say the inverse of this thing, and I'm going to use some notation here, f prime of x. So I'm going to call that the inverse of x. It's going to be 5, 10, 15, 20, and that's going to output 1, 2, 3, and 4. And how do I get that relationship? So all I did was switch my input and my output. What's the opposite of multiplication? Division. It turns out that it's also the inverse. So it turns out that my inverse is going to be equal to x over 5. We're dividing by 5. Or we could call it 1/5 x, right? Same thing. So the inverse of 5x is, or the inverse of multiplying your variable by 5 is dividing it by 5. It switches your domain and your range, right? For each of these, I have actually just switched my domain and my range. My output becomes my input becomes my output. So I'm going to show you how to calculate that right about now. All right, let's go ahead and solve it. I'm not a big fan of Eureka's intro to this, so we're doing our own over here on the side. So I said that f of x was equal to 5x, right? If it was more complicated, it would be difficult for me to actually find that inverse, right? To find what function reverses my input and my output, or my domain and my range. So I'm going to show you how to do this. I'm going to write the steps down a couple times. So my first step is I let f of x equal y. So let f of x equal y. My next step is I'm going to substitute x for y and y for x. Substitute. Step number 3. Solve for y. How do I solve for y? Just divide both sides by 5, right? And step 4 is going to be use proper notation. And I told you that what this means, this thing, f to the negative 1 power, I'm never going to say f to the negative 1 power. I'm going to say f inverse of x, okay? So that f to the negative 1 power x is actually f inverse of x. Eureka does not use that notation anywhere, but when you get into your college courses, you will see that notation everywhere, and I want you to see it now. I don't want college to be the first time you see it. So we're going to use that notation even though Eureka doesn't. Okay. I guess for the sake of not leaving any blanks unfilled, because I don't like it, I can't do it. I have to fill in the blanks. We'll fill in these blanks. What are we doing? We're reversing our x and our y. That's what our inverse does. So this one is this one, right? So then the rest of them, if we go from left to right, would be 3, 1, and then 15, 2, and then 8, 3, 9, 9. How can the points in set G be obtained from the points in YF? You can switch domain and range. Or input and output. Or you could say it X and Y. Right? You can say that in 3 different ways. Not really sure what they were trying to do with this dialogue with Peter, but it's not a very cool answer, so we're just not going to do it. We have time constraints. Okay. Let's find some inverses. We get to do some fun algebra. If you haven't noticed yet, I really like algebra. All right. So for the first one, I'm going to go through the steps, write it down, and then we're just going to rock these out. We're going to graph each one as well on our handy-dandy graphing calculator, because they look kind of cool. So step 1, let f of x equal y. Step 2, substitute x for y and y for x. You could also say let x equal y. So that's done. Step 3, let's go ahead and solve for y. All right, cool. So I'll subtract 1 from both sides. I have x minus 1 equals negative 4y. I'll divide both sides by negative 4, making sure that I divide that whole side by negative 4. I can break that up and call that negative x over 4 plus 1/4, right? Because I wind up with a negative over a negative equals y. And that's good, but I would prefer to write it with the coefficient so that it looks like negative 1/4 x plus 1/4 equals y. And then step 4, we're going to use proper notation. So, in other words, that means that f inverse of x is equal to negative 1/4 x plus 1/4. Let's graph those bad boys. Yeah? All right. Give you all the time. Let's graph this thing. So it was 1 minus 4x, yeah? And the other one was negative 1/4 x plus 1/4, is that correct? Those are the two functions? I'll be able to see it. What did I do? Oh, stupid. My bad. I used the wrong symbol here. And if we look at this graph, we can see clearly the domain and range are switched by looking at these two specific points. Right here I have a point. Right here I have the points 1, 0, right? And this one has the point 0, 1. So the domain and the range, the x and the y values, have been flipped with those. See? All right. Let's do another one. And now I'm not going to write what the steps are. We're just going to go through it. I'll say them, okay? So let's find the inverse of f of x equals x cubed minus 3. Step 1, let f of x equal y. Step 2, substitute x for y and y for x. Step 3, let's solve for y. This one will take a little while. I will add 3 to both sides. And then I need to take the cube root of both sides, right? If I want to get rid of that cube. All right. You might ask, right? How come when I take the square root of both sides, I consider both positive and negative the square root, right? And I've marked you off for that. But I'm not doing it now. And the reason is that we only need to do that for even powers, right? So if I take the square root or the 4th root or the 6th root, I do need to consider that. But for odd powers, I don't. And the reason is this. Negative 2 to the 3rd power is negative 8, right? Because negative 2 times negative 2 times negative 2 is negative 8. And 2 to the 3rd power is positive 8. So it's not the case that I get the same answer when I cube negative 2 and positive 2 the same way as it does when I square negative 2 and positive 2, right? Negative 2 squared is 4, and 2 squared is also 4, right? So you don't have the same relationship going on. All right? All right. Now let's use step 4. Let's go ahead and use our proper notation. F prime of x is the cube root. I'm sorry, f inverse of x. Sorry about that. Prime of x. Awesome. We found the inverse. Let's go ahead and graph these things and see what they look like. What does it look like when I switch the domain and range of a cubic function? All right. Sorry. Minus 3? Yes, thank you. And this is. And I'm going to go ahead and do this in such a way that if you had a TI-83, or, yeah, the 83 plus, right? This one doesn't have a little button where you can go in math and it'll let you put a different root. But remember, we can use our properties of exponents to do this. I could call it x plus 3. Can I just go to the 1/3 power? And guys, if you are doing this, it's the same thing as the cube root. If you are doing this on an 83, you gotta make sure that your 1/3 is in parentheses, or else it'll go x plus 3 to the first power divided by 3, and you don't want that. You want to go to the 1/3 power. And they're kind of fun. I like these graphs. I think that they're aesthetically pleasing. I hope that you're. All right. You guys are math ninjas. Isn't that right?
I'm sorry, don't get it.
Huh?
I'm sorry, don't get it.
Really? No, you can become a math ninja. One day, I'm going to call you my ninja. Alright. Oh, it just got more interesting, guys. Here we go. Let's do this. Step number 1. Let f of x equal y. Step number 2. Substitute x for y and y for x. Look. Large. No, okay. Now let's solve for y. Easier said than done, right? Y is stuck in there quite handily, isn't it? We got to get it out. How do we get it out? By turning this into an exponential equation. Right? But first thing I want to do is I want to get this 2 to come out. If it comes out to the front, it's going to multiply my 3, right? And now I'd like this 6 to go away before I take the log of both sides, before I rather write it as an exponential function. Equation, I should say. So I'll divide both sides by 6. And now it's ready, right? I have just the log on one side and then one term on the other side. So I can say 10 to the x over 6 power equals y, right? I can use that property of logarithms to write it as an exponential equation. So this says 10 to the x over 6 power equals y. And there we go, we solved for y. Let's use our proper notation by saying that f inverse of x is 10 to the x over 6. And let's graph both of these. It's going to be pretty. Or gnarly. I don't know if it's going to be gnarly. It's going to be pretty. I don't think that things that are gnarly are necessarily pretty. I actually think they're not. Oops. That says plus. That's not good. Divide. Okay. And our function was 2 log base 10 of x squared.
No,
Whoa!
3. 3 log.
Oh, thank you. I'm glad you guys are watching. Let's graph it. Alright. Yeah, okay. I'm not a big fan of Eureka's first example of the inverse of a log, because we have this thing going on here. First of all, let's talk about the red graph. Why are there 2 of them? The answer is, because we have x squared in our logarithm, we actually can have negative values for x, right? Because if I plug in -2, I get positive 4, right? So that's why I have this weird fountain of logarithms here. I don't know, it looks like a fountain. It's actually kind of a bad example to use as your first example. So go ahead and ignore the red graph that is to the left of your y-axis. And let's look at these 2. They look like reflections, right? They look nice. It looks better. It's a good example of switching your domain and your range. And we'll get a better example as we go. These are fun to look at. All right, let's do another one. Ooh, now we've got a nice one, okay? We've got an exponential function. We're going to go ahead and find the inverse. It's going to turn out to be, what do you think? Okay, we'll get to that then and we'll find it out. We'll discover on our own, if you're not sure yet. First of all, we'll let f of x equal y. Then we'll substitute our x for our y and our y for our x. And now we've got to solve this thing for y. All right. Normally, or when we first encountered these exponential functions, or exponential equations, and we had to solve them, we wanted to make our bases the same, right? But there's no way I can make this x be a base 2. It's impossible. So my only option now is to take the log of both sides. Remember, we can do that, right? We're allowed to take the log of both sides. I could take any log I want. I could take log base 10. But I'm going to go ahead and take log base 2 because the base of my exponent is 2, and it's going to make a little less work for me. So if you see this base here is 2, go ahead and use log base 2 of both sides, and things will be much better. Log base 2 of 2 to the y minus 3. Now, we need to solve for y. We need to continue our quest, I should say. So solve for y. Yeah. All right, let's continue this one. So, I got to get the y out, but now that I've made it a logarithm, I have a property of logarithms that allows me to take my exponent out. So then this is going to look like log base 2 of x equals, and now I can pull the exponent out. Hey, that's fantastic, isn't it? It's good news. Now y has been broken free. Liberated, if you will. Viva la libertad. and stuff. Okay. America and stuff. All right. Hey, log base 2 of 2 is? Yes. So this just, the log base 2 of 2 goes away, right? It's 1. That's why I chose log base 2. Because it allows me to get rid of that an extra log. If I use log base 10, I would have to leave it there. I'd have to divide both sides by log base 10. It would be weird. It's better to choose this base. Okie dokie. Almost done. All I gotta do now is add 3 to both sides. And then use my notation. Equals log base 2 of x plus 3. That's what we need. It's done. Let's graph it. It's going to be special. 2x minus 3. Alright, so we got 2 to the x minus 3 power. And sorry for those of you that have a 83 or something that doesn't have this operating system. I want to save some time, so I'm going to go ahead and use my log base. I'm not going to change the base. You can change the base if you want. You've done it lots of times now. But I'm going to go ahead and use my log base function. It's x, right? X plus 3. Let's graph it. And you're like, Jesus. That's what it looks like, okay? But you gotta keep in mind, right, that this actually does have this asymptotic behavior down here, right? No kidding. Okay. It's kind of pretty, right? The inverse. So we have our logarithm that, the red is our logarithm and the blue is our exponential function. Kind of fun. Kind of fun. Let's do another one. Another one? Another one. Okay. Rational function. Ooh, we haven't looked at rational functions too much during this class. We'll look at them a bit more in pre-calculus. We'll deal with rational functions a bit more. But hey, let's look at this one. First of all, let's go ahead and find the inverse. We'll substitute x for y and y for x. Ooh, okay. This is going to be tricky. I'm going to multiply both sides by y minus 1. So I have x times y minus 1 equals y plus 1. Multiply both sides by y minus 1. I'm going to go ahead and distribute that x. So I wind up with xy minus 1 equals y plus 1. What are we doing? We're solving for y. It is so weird, right? How do you solve for y with this darn mess, right? What I'm going to do is I'm going to get all my y terms on one side of my equal sign and then factor a y out. That's going to be the trick, right? It is a handy trick. So first thing I want to do is get all of my x and y terms. I knew I made a mistake somewhere. I was like, what the heck? Okay. Minus x. Okay. So then I'll put the y here, the x there. So I just switch that x and that y aside. I moved the x over to the right side and the y over to the left side, changing the signs as I did. And now that I have terms with both x and y, I can factor the y out. And all I need now to do to get y by itself is to divide both sides by x minus 1. So I get y is equal to x plus 1 divided by x minus 1. What the heck? It's the same as what we started out with. Ah, it's like we're lost in the woods. Walking around in circles. Viscosity?
I'm gonna go with viscosity.
The difference between sauce and juice is viscosity.
Well, you buy juice, you buy sauce.
Sauce expires.
When you buy sauce.
It lasts longer, that's true. But now with my case, though, what happens if you water down barbecue sauce and make it less viscous? Does it become barbecue juice? Okay.
Probably put your milk first and then your cereal.
Okay. Here we go. Let's go ahead and graph this. So this was x plus 1 divided by x minus 1. Is that right? I put them in parentheses because my order of operations may be violated. And when we graph this, we can see why the inverse is the same, right? If I was to switch my x and my y, I wind up with the same exact thing. Because this part actually is the inverse of this. You know what I mean? The one that's in quadrant 1 is already the inverse of this one that's almost in quadrant, right? All right. Moving right along. It's pretty special. Actually, we're going to have to wrap this one up tomorrow.